Hello everyone, in this video I'm going to solve 3 example problems on Nyquist sampling theorem. So what does the theorem say? It says that if you have a bandwidth of a signal, and the signal is continuous, and you'd like to sample this signal, then in that case the sampling frequency has to be at least twice as much as the bandwidth of that continuous signal. Okay? So if you're given, have a look at the first problem. You're given a sampler, and its input is a continuous time signal, and its output is a discrete time signal, and I found out that the discrete time signal is cosine pi over 4n. And the sampler is sampling with a sampling period 1 millisecond. But I do not know what the input frequency is. I know that it is a cosine, but I do not know what the value of the input frequency is. So I'm going to denote it by omega node, and I'd like to find what the omega node is. That's the first requirement in the problem. Okay? Of course, you do not need to calculate the sampling frequency in order to calculate this omega node, but I'm going to need it later on, so that's why I calculated the sampling frequency. It's in radians per second. Omega s is equal to 2 pi multiplied by fs, and fs here is 1 kilohertz coming from this value, the inner reciprocal of this value. Okay? Okay, let's do the math. Let's find out how to get omega node. Omega node, if you would like to find it, then since the signal passed by a sampler, then basically what happened is that this signal got sampled, which means that this value is equal to that value. The arguments are going to be the same. So that's why I put this inequality. Okay, and what is the value of t? The value of t is n t, because I've done sampling. So I'm going to cancel n, okay, and thus omega node is equal to 250 pi, after I substituted by t to be 1 millisecond, okay, is equal to 250 pi radians per second. And this becomes the final answer for part 1. Okay. The second part of the problem, it asks me if it's unique or not. Perhaps omega node is not unique. Why? Why do I care? Because if it is not unique, then this is not the only value that could result in a cosine pi over 4n. So I need to take a note of this. I need to make sure that I'm getting all of the possible values of omega node. Could it really be non-unique? Yes, it could. How is that going to happen? Well, if you would like to equate these two signals, then in that case, the arguments, it's not necessarily that the arguments are going to be equated. Perhaps a shifted value of the argument. So in that case, I'm going to put here plus 2 pi n m, plus 2 pi multiplied by an integer. And this integer is, I chose it to be n multiplied by m, because I want the value of n to be cancelled in the entire equation. Okay? What is m? M is basically a value that is equal to, that is an integer. 0, 1, 2, 3, and so on and so forth. It could be -1, -2, and so on and so forth as well. Or perhaps I could add here a negative value. Whether you put a negative or you do not put a negative, it doesn't matter. Why? Because the cosine is even. Okay? If you put here a negative, or you do not put a negative, it doesn't matter. It will matter it will affect the value of omega node. So the value is going to be affected by this negative value, whether you put it or not. But what it is not going to matter is that it is going to be a valid equation. It is one of the possible equations. If you put a negative, that's an equation. If you do not put a negative, that's another equation. And it's going to give you another valid value for omega node as well. Okay? So here, what I have done, I've substituted by m to be 1, putting the negative sign, and I get this value. Okay? Which means that it is not unique. Okay? Which means that omega node is not unique. Okay? And you could find infinite number of frequencies. What does that mean? This means that any frequency that you get from the equation is, when you feed it to the sampler, it is going to give you cosine pi over 4n. Okay? The sampler is not going to distinguish between any of them. All right. The third requirement is to see if Nyquist's theorem has been satisfied or not. Okay, so at omega naught is equal to 250 pi radians per second, what is the value of omega s? Well, omega s, I calculated that to be 2000 pi radians per second, which means that omega s over 2 is less than, omega s over 2 is greater than omega naught, which means that it is satisfied. Nyquist has been satisfied. Okay, so which means that Nyquist, if you feed a signal with frequency omega naught, then in that case the signal is not going to be distorted. Right? On the other hand, if you feed it with a value omega naught 1750 pi radians per second, omega s, the sampling frequency, is much less than omega naught, which means that it has not been satisfied, which means that the signal is going to be distorted. You're not going to have a signal, you cannot reconstruct the signal back again. Okay? And that's the efficiency of Nyquist sampling theorem that we had here. Okay? It tells us whether the signal can be reconstructed or not. If the omega node was very small compared to the sampling frequency, then in that case Nyquist is satisfied and you can reconstruct the signal. If not, then not. Okay? And if I'd like to plot this on the frequency domain, which is not required, then in that case I'm going to see that omega node is satisfied. Okay, why? Omega node is satisfied when it is 250 pi. Why? Because omega s over 2 is 1000 pi. 250 pi is less than 2000 pi, is less than 1000 pi. But when it is 1750 pi, then in that case it is not satisfied. And this is why this cosine is basically not going to be reconstructed back again if it was sampled with that low sampling frequency. Okay? Let's have a look at the second problem. The second problem is similar, okay? And it is it's asking us to find the sampling frequency given the signal frequency in the continuous and in the discrete. We would like to find what the value of t is, okay? And find whether it is unique or not, okay? So again, I equated the two arguments. I end up having t is equal to 1 over 12,000 seconds, which means that fs is equal to 12 kilohertz. Okay, and it is not unique. Why? Because if you put the 2 pi n m and put the value of m is equal to 1, then you get t is equal to 5 over 12 kilo, and the unit is in seconds, right? And this is why it is not unique. The equation is satisfied again. Okay, let's have a look at Nyquist. We would like to verify Nyquist. Okay, so if you verify Nyquist, let's first do the plotting for both, for the case of the t equals 1 over 12 kilohertz. Okay, how do we plot that? Well, you have a 2 kilohertz signal, and that's the continuous signal. Why is it 2 kilohertz? Because fs here is equal to 2 kilohertz. Okay, then in that case you have 2 and -2. These are the two deltas, right? And if you would like to sample it, then you need to repeat it every 12 kilohertz. Okay, so the 12 kilohertz is the sampling frequency, and this is why I have repeated it every 12 kilohertz, right? And this is why I got these replicas, right? But remember, if I'd like to use the convention to do the plotting, then I need to divide by fs. Okay, divide by fs, divide the entire axis by fs, which is equal to 12 kilohertz. And this is going to give you the convention, right? The conventional way of plotting the frequency domain of the repeated signal, okay, of the discrete signal. Of course, this is not mandatory to be plotted. It's not asked in the question, but that's that's a way of visualizing the signal in the frequency domain. Okay, and remember we got here 1 over 6 because cosine pi over n over cosine pi n over 3 is equal to 2 pi is equal to cosine 2 pi 1 over 6, and this value is the frequency. Okay, so this is the discrete signal, and this is the discrete signal in the frequency domain. Okay, which means that you'll get a value of the two deltas at 1 over 6, and the unit is normalized frequency domain. Okay, this is the normalized frequency domain. Okay, let's look at the third part of the problem. We would like to verify Nyquist sampling theorem, whether it holds or not. When the case it's equal to Fs equals to 12 kilohertz, the Nyquist was satisfied, and when the case of 12 over 5 kilohertz, which is 2.4 kilohertz, Nyquist was not satisfied. Okay, Nyquist was not satisfied, which means that I cannot reconstruct the signal if I sampled the signal with 12 over 5 kilohertz. All right, let's have a look at a more difficult problem. You have a sine and a cosine added together, and that's in the continuous signal, and you got the discrete signal, which is the output of the sampler. You got a sine and a cosine, and I'd like to find out what the value of the sampling time is. Okay, I do not know what that system is. I'd like to find out, and all what I know about is that it is sampling with a certain sampling time. I need to find out what the sampling time is. Again, you need to work out the arguments. The arguments need to be equal. Shall I work out the sine or the cosine? I need to work out both. And I need also to make sure that I choose the values of t that coincide with the sine and the cosine arguments. So the value that I get from here, I need to make sure that I got it from here as well. Okay? So when you do the math, if you look at the value at m equals 0, you get 1 over 100 seconds. Okay? And that's the same value that you get at m equals 0 as well for the case of the cosine. But for the case of m equals 1, you get 11 over 100, but you do not get it at m equals 1 for the cosine. Okay? And that's why this value does not work. Okay? So when you choose the value for t, the very first value is t equals 0.1 milliseconds, 0.1 seconds, but you cannot claim that the second value is 6 over 100 seconds. Okay? Because you did not obtain it from the sine. The value for the t has to be you need to get it from the cosine, and you need to get it from the sine as well. And that's why 11 over 100 is going to work only because I was able to get it at the cosine as well. Okay, at m equals 2. I do not have to have these two values to be equal in order for it to work. I need to have the t to be equal. As long as there exists a value for m that makes t equal, okay, a value for m for the cosine and perhaps a different value for the sine that makes t equal, then this is what I'm looking for. Okay, so obviously it is not unique, and it holds, the Nyquist theorem holds for the case of fs equals 100 hertz, but it does not hold for the case of fs equals 9 hertz. Okay, this does not hold. Okay. Thanks for your attention, and please let me know if you have any questions. As a note, this document and this notes is mentioned in the description. Have a look at it, and there's a link for that. And there's a link also for the Arabic version of this video.